Hi, I'm Sean from the Robo Mechanics Lab at Carnegie Mellon, here to present our ICRA 2024 paper titled Pay Attention to How You Drive, Safe and Adaptive Model-Based Reinforcement Learning for Off-Road Driving. This work was done in collaboration with Hanhao Zhu and Professor Aaron Johnson. During autonomous off-road driving, robots need to be considerate of their dynamics in order to enforce safety constraints. Driving too fast or taking too sharp of a turn may cause the robot to lose traction or roll over. However, accurately considering dynamics in unstructured off-road environments can be difficult. In such environments, dynamics can be highly complex and certain physical attributes such as friction may be unknown. While dynamics or controls could be learned directly, doing so often requires large amounts of training data. Collecting such datasets is often too time-consuming and resource-intensive to be practical. To further complicate the task, off-road driving often involves transitioning between different types of environments such as mud, loose soil, or gravel, each of which has their own effects on the robot's dynamics. Part of work has used domain randomization to tackle some of these challenges. In these approaches, a policy for the real-world system is trained solely in simulation. During policy training, simulated dynamics are randomized in order to increase robustness of the learned policy towards variations in system dynamics. As a result, the learned policy is effective in the large range of dynamics, including the real-world dynamics. However, this approach sacrifices performance for robustness, as the policy isn't tailored towards any specific target system dynamics. Ideally, what we want instead is a balance between robustness and performance. In low data regimes where the robot is unsure about specific dynamics, we want its policy to be robust across a wide range of possible dynamics. However, we also want the policy to be able to adapt, so as the robot collects more data and gains a better understanding of its dynamics, it can improve its policy's performance. We propose a novel sim-to-real transfer method that balances robustness with adaptability. In this approach, we simulate many different variations of the given robot morphology by randomizing simulation parameters such as friction coefficient, inertial terms, and motor torque curves. We collect training data on all these systems to train a system identification transformer and an adaptive dynamics model. These two neural networks work in tandem to adapt to any new target system, while also capturing uncertainty about the system's particular dynamics. Given any available observations from the target system, the SysID transformer extracts an understanding of its dynamics as a succinct context vector. Then, given this context vector understanding, the adaptive dynamics model makes probabilistic predictions for the target system. These predictions capture uncertainty inherent in the stochastic system, as well as due to having insufficient observations leading to an ambiguous understanding of its dynamics. Online, we use an uncertainty-aware MPC approach, specifically risk-aware MPPI, to find robust actions given the probabilistic predictions. By considering uncertainty, the robot is able to drive safely even upon initialization when observations are unavailable. Then, as the vehicle drives and collects more observations, it improves its model's understanding of dynamics and in turn the performance of the overall policy. In our experiments, we trained a system identification transformer and an adaptive dynamics model a priori solely in simulation, and then used them to adapt to new systems with unseen dynamics both in simulation and in the real world. We used the adaptive dynamics model within risk-aware MPPI to drive the vehicle down different randomly generated tracks and measure the resulting performance and safety of the policy. To measure performance, we recorded the lap time across systems, and to measure safety, we recorded the number of times the robot violated one of the task constraints. As one of our baselines, we compared using our adaptive model for controls compared to training a neural network dynamics model for each new system from scratch. In this experiment, we randomly generated new tracks for each system and iteratively ran the current policy to collect more data for either adaptation for our method or model training for the baseline method. We fixed the two models at different amounts of training data and tested their performance on a new track. The graph on the right shows the performance and average number of constraint violations per run for the two different approaches. Note the difference in x-axis for the two methods. The baseline method was unable to finish the track given limited amounts of data, so we were only able to start recording performance at 500 time steps of data. Furthermore, it took much more data to improve performance. In comparison, our approach of using an adaptive dynamics model was able to safely drive the robot even upon initialization with no data. And it was adaptive and showed improved performance after collecting minimal amounts of training data. It converged to the system's performance limits by 500 time steps of data and had similar performance to the baseline method given 5,000 time steps of data. We also tested our approach for adapting to different real-world systems. In this experiment, we varied the dynamics of the vehicle by driving over different types of terrain, alternating between high-friction rubber wheels and low-friction plastic wheels, and also artificially changing the motor control parameters to change the aggressiveness of the robot's throttle and steering. As a baseline, we trained a fixed dynamics model trained in just one simulation environment that we tried to best approximate the real-world system. The baseline resulted in dangerous driving when transferred to a real-world system that could only complete the track without any constraint violations 40% of the time. In contrast, our approach was able to complete 50 different runs on 10 different systems without any constraint violations. In total, we ran both methods on 10 different systems. For each system, we did 5 runs on the same track. For our approach, we adapted the dynamics model at each time step using all prior collected data over all previous runs. Our method had better performance upon initialization with no constraint violations and faster lap times. And it was able to adapt to each particular system, showing improved performance in successive runs. Thank you all for listening. For more information, please refer to the paper and please feel free to reach out to us at the conference